Hi, great tops. Thank you for joining me once again. We are still continuing with probability sessions, and today we're going to be focusing on contingency tables. Okay, so what are contingency tables? So contingency table is another tool for keeping record of the counts, right? Or the percentage in probability problems. So they're especially helpful in figuring out whether events are dependent or independent. So you just use contingency table, right? So in this session, you'll be studying a two-way contingency table where we count the number of outcomes for two events and their complement, right? Making 4 events in total because it's a two-way. You have your row and you have your columns. So a two-way contingency tables will always show the counts of the 4 possible combination of events, right? As well as the total for each event and its complement. So we can use contingency table to compute the probabilities, very important, of various events, right? By computing the ratios between the counts and to determine whether events are dependent or independent. Very important. Let's just quickly go and look at an example of a contingency table and try to solve those probability questions. Let's quickly take a look at this example. It's adapted from Feb March 2012. It was your question 5 from this paper, and they've given you a table. We call this table what? Contingency table. As you can see, there are 4 events. There is male, there's female this side, there is do not play sport, there is play sport, right? And the total, right? It also shows you the total number of males, right? Those ones who do not play sport, 51, plus those one who play sport, 41, and the total will be what? 100, right? So also showing you the females who do not play sport plus those one who play sport, the total is going to be 136, right? Also showing you those one who do not play sport, the total is 120, like that, right? So we call this a what? A contingency table. Let's just go and calculate and learn how you can actually calculate these questions. All right. They're saying the sports director at a school analyzed data and determine how many learners play sport and what gender of each learner is. The data is presented in the table below. We call this a what? Contingency table. 5.1, they want you to determine the probability that a learner selected random is a male. So what do we know about probability? Probability will take the what? The number of favorable outcome divided by the total number of sample space. All right. So we want probability that a learner chosen at random is a what? Is a male. That is the total number of males divided by the total number of what? Of sample space. All right. What is the total number of males? It's 51 plus 49, right? It is in this row, which gives us a total of what? Of 100, all divided by the total number of sample space. You get your total number of the whole sample space at the bottom corner. All right. So because it's the total of all those combination of the events, like the one who do not play sport and being a male and female, the one who plays sport and being a male and female, right? When you add the two, you get the total number of those things. So it's going to be 100 divided by what? Divided by 236. So this will give you what? 25 over 59 as your answer. Let's go to 5.1.2 now. So 5.1.2, they want you to determine the probability that a learner selected random will be a female and what? And plays sport. So it means that this is the probability of female and what? And what? Play sport, right? Play sport. All right. Let's go and check now. The one for female, let me just highlight it for you. So the one for female is this row, right? Is that row? but we want the one who also what? And play spot. So and play spot will be which one? This one. Can you see? So it's female and play spot. It's gonna be what? It's gonna be 67, right? 67 out of the total number of sample space, which is what? 236. So you just say 67 divided by 236, then you finally get your answer. So it's just gonna be 0.28, right? So we can just leave it like that. Okay, let's go to 5.2. In 5.2, they are asking you that are events male and do not play sport mutually exclusive? Use the values in the table to justify your answer. Are the events male and play sport mutually exclusive? What happens if they are mutually exclusive? That is, they cannot occur at the same time. There is no intersection, right? So in other words, they don't have something in common. That is, the probability of A and B must be equals to 0, right? So let's just go and check what is the probability of male and do not play sport. Let's go and trace that, right? Probability of male. So for male is this row. Let me just use yellow one. Is this row, right? And do not play sport is which one? Is this one, right? Is 51. So there is a certain value there, right? Meaning that probability of male and do not play sport. So it's do not play sport. It's gonna give us what? 51 out of what? 236. This is not 0, right? So can we answer the question now? Are the events male and do not play sport mutually exclusive? The answer is what? Is no. And why are we saying no? It is because the probability of what? Of male and do not play sport is not equals to what? Is not equals to 0. Meaning that there's actually intersection between the two. If they're mutually exclusive, there is no intersection. But in this case, we can see there is intersection. 5.3, very, very important question. In contingency table, there's no way you can't find this question, the last one, right? Mostly because contingency table are mostly used to check if two events are independent or dependent. Okay, so let's just go and do 5.3 now. Okay, so for 5.3, they are saying are events male and do not play sport independent, right? Are they independent? Are events male and do not play sport independent? Show all your calculation to support your answer. How are we going to prove whether they are independent or not, right? So if they are independent, right, we must get that the probability of male and do not play sport must be equals to the probability of what? Of male times what? Times probability of what? Of do not play sport, right? So they must be equal if they are what? If they are independent. So we have already calculated the probability of male and do not play sport, right? It was what? Let's go and check again. Male and do not play sport. It was 51 out of the whole total sample space, which is what? 236, right? So this is the same as 51 over 236 will be the same as 0.216. Okay, I'm just gonna round it off to 3 decimal place. Let's go and calculate probability of male and we multiply it with probability of what? Of do not play, right? So probability of male, how many total males do we have? So we have a total of what? Of 100 of them. So it's just gonna be 100 out of 236. We multiply with probability of do not play sport. Here is it, right? It's this coulomb here, and its total is what? It's 120 out of the whole total of what? Of 236, right? So you're just gonna multiply the 2 and we get the answer. Okay, so it's giving me 0.215. If we round off to 2 decimal places, it's gonna be 0.22, right? Even if you round this to 2 decimal places, it's gonna be 0, what? 0.22. Okay, can you see that now we can finally deduce that therefore, just look in red color, therefore the probability of male and do not play is equals to the probability of male multiplied by the probability of what? Of do not play, right? Because both of them are equal to 0 comma what? 0 comma 22. Then what does it implies? It implies that male, the event of male and do not play sport is what? Is independent. So the event is what? Is independent. What does this mean in real life? It means that the fact that you are a male uh, does not necessarily tell us that you do not play sport, right? Or rather, the fact that you do not play sport does not actually tell us your gender, right? We can't say because someone do not play sport, then that person is a male, right? We have females who are not playing sports, right? So it's actually something that's also applicable in real life, right? So we have now proven that indeed these two events are what? Are independent, right? They don't influence one another. The fact that you are a male cannot tell us that you do not play sport, because we have males who play sport, right? So in other words, they are really what? They are really independent. And we have just proven it using probability and probability calculation for independent events. Okay. Okay, let's now quickly focus on this different example. All right. So you're given a contingency table that is not complete, right? They tell you that the total in a survey of 1,530 sky drivers, and you can see it at the bottom corner, right? So that's your total number of sample space. We're asked if they had broken a limb. The results of the survey is as follows. 5.1, they say calculate the values of A, B, C, and D, right? You need to calculate this using your contingency table. Okay, look at this. Quite interesting. Very, very simple. You have 433 plus A. We know that it will be equals to what? 913. So to solve for A, we're going to say 463 plus A must be equals to 913, because that's the total, right? So you'd say 913 minus 463, then it will give us what? 450, right? Meaning our A will be 450. So where there is A, I'm just gonna put 450. When you add 450 and 463, you must get 413. Okay, how are we gonna solve for B? Look at this here. So to say 463 plus B is equals to what? 782, because that's the total. Meaning that our B will be 782 minus 463, which will be what? 319. Okay, so it's just going to be 319. So where there is B, we can say 319. Okay, let's go to C now. So to solve for C, you can say 319 plus C is equals to a total of what? Of 617. Meaning that our C will be 617 minus what? 319. Which will give us what? 298. Okay. So we are completing the table. Let's go and calculate our D, last one. So it's going to be 782 plus D is equals to 1,500 and what? And 30. So D will be 1,530 minus 782, which will be what? It will be 748. Okay, we have finally calculated all the values of A, B, C, and what? And D. Very quite simple. Okay, let's go to 5.2 now. 5.2 want you to calculate the probability of choosing a random at random in a survey a female skydriver who has not broken a limb, right? So they want you to calculate this probability of choosing a female skydriver who have not broken a what? A limb. Okay, so how are we gonna get that? So you're just gonna use your table in order to determine that, right? In order to determine that. Let's go and check a female skydiver who has not broken a limb. Let's go and trace that. must be a female skydriver who has not broken a limb. So it's C, right, which is 200 and what? And 98. So the probability will be equals to 298 all divided by 1500 and what? And 30, the total number of sample space. So 298 divided by 1530, which is the same as 149 over what? Over 765. Right? You can convert that into decimal or in as a percentage. Okay, very interesting question. You'll always get this question in your contingency table. There's no way, right? Because that's why contingency tables are used. They are actually used to determine whether events are independent or dependent. Okay, let's now go to 5.3. Okay, so 5.3, right? They're saying, is being a female skydriver and having broken a limb independent? Use your calculations to actually motivate your answer. Round up to 2 decimal place. Okay, so how are we gonna prove whether they're independent or not? We're just gonna go and calculate the probability of being a female and what? And a what? And having a broken limb, right? Having a broken limb. Okay, so let's go and calculate being a female and having a broken limb. It's what? It's 450 degrees out of what? The total of what? Of 1530. They say round off your answer to 2 decimal place. We're just gonna round off to 2 decimal place. So it's gonna give us 0.29. All right. Let's move. We now go and calculate the probability of what? Of female multiplied by the probability of what? Broken limb, right? Because we want to check whether they are independent or not, right? If they are equal, those things, they'll be independent, but if they are not equal, they won't be independent. In other words, they'll be dependent. So probability of a female, how many females do we have in total? It's 450 plus 298, which is 748 over 1530 multiplied by the probability of having a broken limb. What is the total number of people who have broken limbs? It's 913, right? And 13 over 1530. Okay, just gonna use a calculator to multiply that and convert your answer into decimal place. Okay, so when we calculate, we are getting 0.29 also in 2 decimal place. See something interesting here. Probability of female times broken limb is 0.29. Probability of female and broken limb is 0.29. What can we conclude? That the probability of being a female and broken limb is actually equal to the probability of female multiplied by probability of what? Of broken limb. Okay, because both of them are equal to 0.29. What does it conclude now? It concludes that therefore these two events are what? Are independent. Okay, because they are equal, right? This one is equal to this, and this is the rule for independent events, right? They're independent. Let's go to the conceptual understanding of this, right? So being a female skydriver, right? It's actually, or rather we can say, having a broken limb does not necessarily tell us that you are a female skydriver. You can be a male, right? In other words, the two events are independent. They don't influence one another. Okay, just for you, because you are a female skydriver, does not mean that you have a broken limb, right? In other words, the two events are what? Are independent. All right. All right, so here's your quick activity. I would like you now to pause this video and try to answer these questions, right? That wants you to get the probabilities, right? Drop your answers on the comment section and I'll just come and comment from there. And let's see how this goes. All right. Okay, let's now quickly focus on this example. Quite interesting, quite challenging a bit, but hopefully be able to learn something after we are done with this session. Okay, so they are saying use the contingency table below to answer the following questions. Okay, number one, they said what is the probability that a learner from grade 11 has a cell phone, right? So a lot of misconception with this question can be, okay, this is just a learner from grade 11 having a cell phone, then you go and trace it and you say probably maybe 59 out of the whole total sample space, which is 118. And this is incorrect, right? You must be very, very careful when solving contingency table probability questions, right? Because they can put some little tricks there where you find that this whole sample space is not actually the total number of sample space within that question, right? You must be able to deduce now to say, where should I divide by the whole sample space? Or rather understand what the question says, right? So this question really, it says, we are finding the probability that a learner is from grade 11, right? In other words, our total sample space will be all learners in grade what? In grade 11, because we are not going to grade 12. But we are saying from grade 11, we want the probability that a learner has a what? Has a cell phone. So that's the trick part of this question, right? So they use the word from, and sometimes they can use the word given, right? Given that the learner is from grade 11, you can see by those key terms that, oh, actually, we're not supposed to divide by the whole sample space, but rather the sample space for what? For grade 11 learners or whatever event they give you. Okay, so we're just going to calculate this probability. So the probability that a learner from grade 11 has a cell phone. How many learners have a cell phone in grade 11? It's 59 of them, right? But the sample space, these are all learners in grade what? In grade 11, because they said all learners from grade 11. Okay, so our total there is what? Is 65. So be very careful with that. Okay, let's go to number 2 now. So with your number 2, they are saying, what is the probability that a learner who does not have a cell phone is from grade 11? Another trick. Look at this. What is the probability that a learner who does not have a cell phone is from grade 11? Okay. What is that probability? That a learner who does not have a cell phone, right, is from grade 11. So what is the total number of sample space here? It's all learners who do not have what? Who do not have cell phones. Be very careful with that, right? So all learners who do not have cell phones will form our total number of what? Of sample space. Because they said, what is the probability that a learner who does not have a cell phone? How many learners do not have a cell phone? But from those learners, we want that probability that the learner will be from what? From grade 11, right? How many of them are there in grade 11 who do not have cell phone? Is 6. Out of how many who do not have cell phones? Out of 9, right? So I think we can simplify that. Then it will give us what? 2/3. So be very careful when solving contingency problems like these ones, because it's not always the case that you need to divide by the whole sample space, but rather understand the question. They will tell you that we are choosing from these specific learners, right? But then you can be able to deduce that. Okay, let's now go to the last question. Like I said, in all contingency table, you can't miss this question, right? Because basically contingency table actually help us to determine whether or not events are dependent, right? Or rather independent. Okay, so we use them. So that's why you can't have a contingency table question without this question. Okay, so they're saying, are the grade of a learner and whether he has a cell phone or not independent events? Explain your answer. So in maths, we give mathematical explanations, right? You don't explain in words. You say, no, I think they are independent because of 1, 2, 3, 4, 5. No, we represent that mathematically by calculations. Okay, so what happens if two events are independent? If A and B are independent, we have already talked about this in the previous session, right? Independent. Okay, what happens? Probability of A and B will be equals to what? Sorry for the background sound. So the probability of A and B will be equals to what? Will be equals to probability of A times probability of B. Okay, so that's what we know about independent event. Now we need to go and check that the event of a grade, right? And whether Elena has a cell phone. So we have this event has a cell phone, and we also have the grade. But the problem is we have two events for grades, right? We have grade 11 and grade 12. And now the question is, how do we now go and use the one for grade, because we have two of them? So what you basically do is you choose one of them, right? Sometimes they will give you questions where they just tell you those events such that there are two of them. So what you do is you choose one of them and you use it to actually show whether or not they are independent or not, right? So I'm just going to choose grade 11. So I will say probability of grade 11 and what? And has a cell phone, because this one we are given has a cell phone. Cell phone. Oh, sorry about this. Cell phone. And we're going to calculate that. And we're going to go and calculate probability of grade 11 times probability of what? Having a cell phone. Okay. So because we need to calculate probability of A and B and check whether it's equals to probability of A times probability of B. Okay. So probability of grade 11 and cell phone. Let's go and check. Elena in grade 11. Grade 11 and cell phone. Here is it. It's 59, right? But in this case, we are not saying from grade 11, right? We're just a probability that Elena, grade 11, has a cell phone. It's 59 out of the whole sample space, which is what? 118. So there's a difference between when they say from grade 11, right? So let's go and calculate probability for a grade 11 learner, that Elena is in grade 11, is 65 out of the whole sample space, which is 118, right? Multiply by probability that Elena has a cell phone. How many total of them? It's 109 over the whole sample space, right? So we're just going to simplify this and see if it's the same. 59 over 118 is same as 1 over 2. But 65 over 118 multiplied by, what's this? 109, right? This is 109. 109 over 118 is going to give us 7085 over 13924, right? Can you see that these two are not the same? We can conclude now that probability of grade 11 and cell phone is not actually equals to probability that Elena is grade 11 times probability of cell phone, right? When they are not equal, it means they are not independent, right? So it means we can now conclude that therefore having a cell phone and being in grade 11, they are what? Not independent, right? Actually, in other words, they are what? They are dependent, right? They are dependent events. It means that the fact that Elena has a cell phone can actually tell us that really they're in grade 11, or the fact that Elena is in grade 11 can tell us that what? That actually the Elena has a cell phone. Okay, so that's what we can conclude from there. Okay, not independent because probability of A and B was not equals to probability of A times probability of B. That's basically how you go about that question. All right, grade 12s. Thank you very much. That's the end of our session. Thank you very much for joining. Thank you very much for watching this session. I hope you learned something. Don't forget to write the quick interactive activity. Just drop your answers on the comment section and I'll just respond from there. Okay. Otherwise, for today, that's all for me and goodbye.